We're going to look at the last chapter in this semester's chemistry. And it's a continuation of our discussion of chapter 8 on bonding. And this is going to focus principally on covalent bonding. As far as the handouts go, for those of you who are not here in person, I've only handed out PowerPoint slides, review document version 2, and the worked problems, and then the chapter 9 crossword puzzle, in case you're looking for it in Brightspace. All right. So let's continue with our discussion of, actually, we're still in the localized electron model of the valence bond theory, which, as a reminder, says that bonding takes place when orbitals overlap between atoms. And the electrons that are coming from those individual atoms still belong to those atoms, so to speak. They share them in the overlapping orbitals, but they still have legal rights to them, so to speak. There's just a problem, though, and this problem came up fairly early on in the 20th century. And our example here is methane. If we use methane as our example, we try to write the Lewis dot structure for this molecule. We have 4 valence electrons here, and 4 times 1 is 4 there. So we have 8 electrons. Okay, so we know through using the VSEPR system that we're going to have a carbon in the middle and then 4 hydrogens like this. 2, 4, 6, 8, we used all of them up. Okay, so, and we also know that the geometry of this molecule should be a tetrahedron because we have 4 groups. Like 4 groups implies tetrahedron. And that's been confirmed. There's physical, chemical evidence for that structure. And the bond angles are going to be 109.5 degrees. Exactly. Because all of these bonds are equivalent. Okay. So that gives the shape of tetrahedron and the bond angles of 109.5. Okay, here's the problem. If we're going to stay with the localized electron model, then what are the overlapping orbitals? Okay, the hydrogens, of course, they're only going to be 1s's, right? Each one has a 1s. That's not where the problem is, because that's all they have to deal with. The problem is with carbon. If we look at the electronic structure for carbon, which has 6, carbon 6 would be 1s2, 2s2, and 2p2. Okay, and the model also says that we only overlap valence electron orbitals. Right, so we're stuck with these right here. Okay, if you remember, the s orbitals are spherical. That's an s orbital. The p orbitals can point in 3 different directions. Right? If we set up there our x, y, and z, then we have like this and like that, and then on the z axis like that. So we have those possible x, y, and z p orbitals. Okay. So we've got 2 electrons here, we've got 2 here. if we try to overlap, even if we move an electron from here to here, so that we can get four orbitals that can pair up with one from each one of these, you're not going to get equivalent orbitals. You're going to have three like this and then one like that. Okay, so that's the problem. You can't get the known structure for methane from an overlap of these valence orbitals and these 1s orbitals from hydrogen. It just doesn't happen that way. So there's a problem with the theory. So what do we do when we have a problem with a theory? Well, we have essentially three choices plus the one that I added for religious purposes. We either modify it, we restrict its use, or we throw it out and start over. At this point in history, the choice was to modify. Okay. Right, so here's the valence configuration for carbon. And there's an explanation in red letters, just what I said. Okay. So the answer to the problem, the modification is called hybridization. And it was proposed by Linus Pauling, the same person that wrote the book on the nature of the chemical bond and got a Nobel Prize and so forth and so on. He proposed this modification to the theory so that we could get four equivalent orbitals that would overlap with the hydrogens and give us our tetrahedral structure. And he did this in 1931. So what Pauling said was, all right, when it's required, when the bonding requires that we end up with a known structure, and in our case, we're talking about the tetrahedron, but it works for others too, and we'll cover those in a minute. But when it's required, then as the molecule comes together, the hybridization is invoked for the central atom. And in this case, we take 1s orbital, right? And we take 3 p orbitals, and we produce 4. We have to have the same number of hybrid orbitals as the atomic orbitals that go into the mix. So we have to have 4 orbitals. So we're going to have 4 that come out of that, and they're going to be hybridized orbitals that we call sp3. So 3 p's and 1 s give us these 4 hybrid orbitals. And these 4 hybrid orbitals point to the apexes of a tetrahedron. And that solves that problem. Now, for us, the concept is the only thing that's required for us to work with it and understand it. But for the chemists who bought into this hybridization, and for Pauling, who's proposed it, there had to be mathematical modifications to the quantum mechanical equations that went into describing this. Remember, you have the quantum mechanical model has 4 numbers, 4 principal quantum number, the angular momentum, the magnetic, and the spin. Those 4 numbers went into equations to give us this model. Okay, so they had to come up with a modification that would work to this end product. Okay, so that's already been done. We don't have to worry with that. Okay, so this sp3 hybridization gives us the structure that we need. And just as a reminder, I mentioned it earlier, this only happens when the bond, the structure is required. Otherwise, we're just stuck with this. But when they come together, then that's when the hybridization occurs. And like I've said before, nature just does what it does. It ends up here. What we're trying to do is make sense of it, right? And it may be right and it may not be right. Okay, so when we look at the relative energies of the orbitals, we find that the s orbital is slightly lower in energy than the p orbitals. Now, their energy range is the same because their principal quantum number is the same, but they are slightly different. The energies for the s orbital is a little lower than that for the p, and we looked at that in terms of penetration. When we discussed penetration, the s orbital has a lower energy than p orbital. But when you hybridize them, what do you get? Well, the simplest way to understand it is, what contribution do you have? Well, this contributes 25%, and these three contribute 75%. So you would expect the sp3 hybrid to be 75% closer to the original p energy level than to the s. So that's what happens when we put the mix together. We expect the energy level to be at about 75% between the two. And this is the when those new set of orbitals were introduced into the quantum mechanical model. This is what the model spit out in terms of potential orbital size and direction. When the hybridization took place from the left-hand side to the right-hand side, now you get four equivalent orbitals. They're pointing to the proper locations in the tetrahedron. Okay, and this is what we end up with as our molecule. And this is artist's conception, of course. Okay, now let's take another example. And there's only a slight twist. And the purpose of looking at ammonia is that ammonia only has 3 hydrogens. And when we put this model together, well, we introduce the idea of electronic geometry versus molecular geometry. Okay. The electronic geometry of ammonia is still tetrahedral. Okay. So what we get is, well, let's go ahead and do it anyway. Let's see, this would be 5 and 3. That's 8 again, 8 electrons. So we have nitrogen, and we have this possibility here, here, and here. And we're going to put a lone pair there, and we put hydrogens here. Right. So that's why this is tetrahedral electronic geometry. When we cover it up, we get a triangular pyramid. But we still, in order to satisfy the electronic geometry, we still need sp3 hybridization for the nitrogen. Okay, and the nitrogen, when we look at the nitrogen molecule, it has 7. So that's 1s2, 2s2, and 2p3. So this would have 2 electrons in it, and this would have 3. But we'd still hybridize, we'd still hybridize those orbitals. We wouldn't put these 2 S's as a pair here, and then say we have 3 here, because that would be trigonal planar. And that doesn't satisfy the model. That doesn't satisfy the reality that physical evidence tells us it is triangular pyramid. So we still have sp3 hybridization, but now a lone pair occupies one of those hybrid orbitals. Okay, so what we've done is we wrote the Lewis structure. We determined its electronic geometry and its molecular geometry. And this is what we end up with. We still end up with sp3 hybridization. And there's an artist's conception of the molecule with a lone pair in that sp3 hybridized orbital here. Now, it still holds that this lone pair tends to balloon because there's nothing on this other side constraining it in the bond, right? So it tends to balloon and it puts pressure on these bond electrons and it squeezes it down. So the bond angle is going to be less than 109.5. Okay, and that's what we observe. Okay. So, let me see, maybe I'll set up a table on the left-hand side. And maybe I won't. Because I've got a slide with the table in it anyway. So suppose we attack this problem using hybridization to help us with C2H4, which is called ethylene or ethene. Either way works. So if we have, and this is a real molecule. I mean, it exists. In fact, this is the one that they use in sterilizing boxes. We used to autoclave everything, right, to get it ready for surgeries. Now they pack them in these plastic bags that are permeable to certain gases, and they stick them in this box and they flood it with ethylene, and it permeates there and it kills all the bacteria, and it's a bacterial barrier. So once it's in the bag, then there's nothing else can get in there. So they use this gas to sterilize the equipment. Okay, so what's the shape of this molecule? Well, if we remember how organic molecules are written, what we're looking at is, well, let's do the valence first. Let's see, 2 times 4 is 8, and then 4 more equals 12 electrons. And the carbons are bound to each other. And the hydrogens are bound to the carbons. This, that. So 2, 4, 6, 8, 10. We have 2 electrons left over. Well, if we put the 2 electrons here, that gives this carbon an octet, but that one doesn't have one. So what we normally would do is take those 2 carbons and make another bond out of it. So now both carbons have an octet, all the hydrogens have their duets. So that's our Lewis structure. What's the geometry? Well, the geometry is assigned to each one of the carbon atoms, right? So we have 1, 2, 3 groups. That's trigonal planar. And since we don't have any lone pairs, that's the molecular also. And it's trigonal planar for both of them because they're identical groups. Okay, so how do you get trigonal planar out of a 2s and 2p's? You don't. You still have to hybridize. So how do we hybridize to get that? Well, as it turns out, 2s's and 2p's, if you want 3 equivalent orbitals, hybrid orbitals, you only need to use 2 of these. Like that. And we start in the low energy and work our way up. So we use this one for sure, and then only 2 of those. So now we get an S and 2 P's. So that's our hybrid orbitals. We get 3 of these, 3 sp2 hybrid orbitals. And there's 1 left over. Right? We have that p orbital left over. Okay. Bond, let's see, shape of the molecule is trigonal planar for each carbon, and the bond angle will be 120 degrees. Right, because it's trigonal planar. Right, that'll be 120 degrees. Okay. Well, what happened to this orbital? Well, if we look at it this way, and we've overlapped, we have like that, with our 120 degrees here, like that, trigonal planar, then we can get an overlap like this, and then this is for the hydrogens with their overlaps, right? Getting kind of busy. And then you have the unused p orbital, right? These p orbitals here. Okay. So we had a pair of electrons there, and they would have been here at first, right? So what we do is we use those 2 and we overlap those p orbitals. Right? Their electron density model would fit on either side of the sigma bond, and these are pi bonds. We talked about that yet? Okay, it's coming. Okay. So that's where the unused p orbital went. It went into the double bond. I think it's coming pretty shortly, actually. We can't, sp3 hybridization won't work because it gives us the wrong bond angles. That's tetrahedral geometry. sp2 gives us the trigonal planar. All right. Here it comes. So we call any bond that's on axis between the atoms is a sigma bond. And you can only have 1 sigma bond between 2 atoms, right? You can't put 2 bonds on the same axis. That density is defined here. But you can have pi bonds, which are off axis. They run parallel. They're not quite as strong, right? Because they're not between. It's like trying to pull a truck out of the mud with a chain. Like you can only have 1 chain between the car and the truck. If you put 1 off axis, it's not going to be as strong. Okay. So that's what the pi bond does. And you can have 1, look at it this way. If the sigma bond is this way between the 2 atoms, then you can have a pi bond in this plane, or you can have a pi bond in this plane. Right, so that's possible. And we're going to look at one in just a minute. All right, you've always got to have 1 sigma bond before you can have any pi bonds. Pi bonds don't occur without a sigma. And while we're here, the energy of the sp2 hybrid is even lower than before, because now we have 3 orbitals, and this one contributes 33%, and this one 33 1/3, and this one is 67%. So the energy level is going to be closer to the S because there are fewer P's to draw it up to add energy. So the energy of the hybrid sp2 orbital is going to be lower than the sp3. All right, so there's the hybrid orbitals, and there's our unused p orbital. And we should have a model coming up. Okay, so there you have it on the 120-degree angles for the sp2 hybrids. And then this is the model of ethylene, where it's showing those dashed lines as the overlap of the unused p orbitals. That means we have 1 sigma and 1 pi only between the carbons. All right. Next problem. Next problem is an example, carbon dioxide. Okay, so carbon's going to have 4, oxygen has 6, for 2 times 6 is 12. So we have 16 electrons we have to use up. So we have a carbon in the middle. We have an oxygen here and here. That's 2, 4. It's 12 electrons. 2, 4, 6, 8, 10, 12. Working from the outside in. Used up all of them. Now, we determined in chapter 8, was it? Yeah, chapter 8. How to tell the difference between this one, that's that, or this one as the preferred Lewis structure. And we determined using formal charge that this was the better option. So we throw this one out and we're back to this one. Okay, so how do you get, well, let's see, the VSEPR says 2 bonds around the carbon, that's 180 degrees, and this molecule is linear. Right? They're no lone pairs, so the linear electronic geometry and the molecular geometry are exactly the same. Okay, how do we get there? Well, we need 2 equivalent orbitals, that hybrid orbitals, that give us a 180-degree bond. So if we're starting from our S and our P's again, we only need 2 of those. So we actually have an sp hybrid that will give us the sigma bonds on either side. And we have actually 2 sp hybrids for carbon. Now, oxygen is going to have to be hybridized too, but we're focusing on the central atom right now. We don't want to make it too complicated. So the shape of the molecule we've determined in the last chapter would be linear, and the bond angles were 180 degrees. So this is our Lewis structure. Okay, how do we get there with hybridization? We really only need to combine 1 s and 1 p orbital. That gives us a linear structure. And the energy then is 50-50, right? 1 of these and 1 of these. So the energy of the hybridized sp orbitals is even lower than the sp2 or the sp3. Okay. So if this is the artist's conception and the generated orbital profile of an sp hybrid, and notice that 1 points in one direction and 1 points in the other direction. So we'll use 1 of those to make a sigma bond on this side and 1 of them to make a sigma bond on that side with the oxygen. So what do we have left over? Well, we have 2 unused p orbitals. Right? 1 of them is in this direction and the other one is back into the board. Okay. All right, let's hybridize oxygen while we're here. Okay, so oxygen has, let's see. it needs 1, 2, 3 hybrid orbitals, which means oxygen will be sp2 hybridized. Right? 2 of these orbitals are occupied by lone pairs, and one of them is used to form the hold on a second. Yeah, that's right. That's right. The sp2 hybrids give us an overlap here with that carbon for a sigma bond. And then these 2 are in the other sp2 hybrid orbitals, and oxygen still has an unused p orbital. So that unused p orbital on this oxygen overlaps with the unused p orbital on carbon in one plane, and then rotate that plane this way, and this one overlaps into and out of the board. Okay, so it can get complicated, but really it's hybridization is not that complex if you break it down into pieces. So what we've got is hybridization for both oxygen and carbon, and the pi bonds are overlapping unused p orbitals. Carbon happens to have 2 unused p orbitals, and each of the oxygens have 1 unused p orbital each. So we get that balance and overlap. Okay, so there's the sp for the carbon and the sp2 for the oxygen overlapping on either side. And that forms the sigma bonds. Okay, so let's move to the nitrogen molecule. We know it's diatomic. And we also know that each nitrogen has 5, so that's 10 electrons. And if we do like this, then that's -2 equals 8, 2, 4, 6, 8. And 2, 4, 6, we still only have, let's see, did I do that right? 1, 2, 3, 4, 5, 2 is 10. Yeah, okay. We want to give each nitrogen an octet. So if we take these 2 here and these 2 here, now we get an octet with a lone pair on each nitrogen. Okay, so each nitrogen has an electronic structure of linear. So put together, we have a linear molecule. And in order to form the sigma bond, we need to hybridize it in such a way that we have linear. Okay, let's see, 1, 2, 3 here. So that we hybridize and get a linear, and to get linear, we only need to combine S and P. So that means we have 2 unused p orbitals. So this one here and into the board, and this one here and into the board. And we get overlap there, and we get overlap here and here. So we have 1 sigma bond and 2 pi's. Just like the carbon, actually, in carbon dioxide. But in this case, we only have 2 atoms in that bonding scenario. And in carbon dioxide, the carbon has a pi bond on one side and a pi bond on the other. In this case, we only have 2 atoms, so both pi bonds have to be between those 2 atoms. All right, so there's your Lewis structure. And we need sp hybridization. And we have 2 unused p orbitals. The sps form the sigma, And then the unused P's form the two pi bonds. Okay, so if each one of these nitrogens is sp hybridized, then it has like this. And you still have the lone pairs out there. Okay, with these overlapping. Right, because, well, actually, that's not accurate. Because two SPs, one SP is in this plane and the other SP is in the other plane. So the lone pairs are in a different set. I was conflating two orbitals into one. Let's see. I hope we have a picture. Yeah, here we go. So there's your nitrogen. It has an SP. Well, actually, I wasn't too far from the truth. One SP points one direction, one SP points the other direction, and you get the SP overlaps to give you the sigma bonds, and the lone pairs are in. So this is one of those SPs. I was right the first time. And this is the other SP pointing that direction. Actually, this SP has a big lobe here and a tiny lobe on that side. And this SP has a big lobe here and a tiny lobe on the other side. So this is where the lone pairs reside, right there. And then we get two pairs of electrons, 4 electrons, forming the pi bonds, overlapping the p orbitals. Okay, so let's, as if our life isn't complicated enough, let's take a bigger molecule, PCl5. Okay, if we do the Lewis structure for this one, this would be 5 here, and this would be 5 times 7 is 35. So we have 40 electrons. And we have a P in the middle, and we have 5 chlorines. Right? 2, 4, 6, 8, 10. So now we have 30 electrons. Well, if we do 6 each times 5 is 30. So we've used them all up. There we go. So what structure does this tell us according to VSEPR? If you have 5 groups, that's a trigonal bipyramid. Okay, which looks something like this. Phosphorus in the middle. Up here we have a chlorine. Down here we have a chlorine, chlorine, and chlorine, and a chlorine in the back. So what bond angles do we have? Let's see, the shape, trigonal bipyramid. We have the possibility of a bond angle here of 180 degrees. We have a possibility of here of 90 degrees. And we have a possibility of here of 120 degrees. Okay. That's what we know from the last chapter. How do you get hybridization that will satisfy these conditions? Well, we need 1, 2, 3, 4, 5. We need 5 hybrid orbitals, right? If we just use an S and 3 P's, that only gives us 4, right? So look where phosphorus is. It's in the 3rd period, right? Remember when, it's in the 3rd period, which means that the principal quantum number is 3. And when you have 3, you have access to S's, P's, and D's. So we have a D here. We only need one of those. That gives us 5 DsP3 orbitals. Okay, that's how we fix that problem. Now in this case, each one is, say, equivalent in shape and energy, but not in orientation, right? Because we get these different angles. So we have to allow for that also. So this is what it would look like. Chlorine doesn't have to be hybridized, I don't think. Chlorine would be, well, it's what would chlorine be? Well, we'd have neon as our core. And then we would come down to 3s2 and 3p5, right? Yeah, 17. So what we're looking at here is we could use these p orbitals to overlap. We wouldn't have to hybridize chlorine. Okay. So that's what happens when you need 5 hybrid orbitals. You have to dip into the Ds. Now we're going to go to the highest number of groups that we've studied so far, and that's where we'll stop. And our example here is xenon tetrafluoride. Okay, so we have 8 for a noble gas. 4 times 7 is 28, and that's 36 electrons. Okay, so we have xenon in the middle. We're going to form 4 bonds with the fluorine, 2, 4, 6, 8. So that's 28, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20, 22, 24. That means we have 4 electrons left over, and they have to go on the central atom. Okay, so when we're looking at the shape, the electronic geometry is octahedral, right? There's 1, 2, 3, 4, 5, 6. We have 6 groups, that's octahedral. But the molecular geometry is square planar. Remember when we drew the xenon in the middle, the fluorines would go on the square. And then the apexes would be occupied by the lone pairs. We know that's true because of various physical measurements. Right? This is a nonpolar molecule. Okay, so how do we get that? We need to hybridize it so that we have 6 hybrid orbitals. Okay, so if we have an S and P, 1, 1, 2, 3, we're short by 2. So we've still got the Ds, right? Especially xenon, right? It's down in the fifth group. 1, 2, 3, 4, 5. We only use 2 of them. So that's 1, 2, 3, 4, 5, 6. So the hybridization is D2sp3. Don't ask me why they put the Ds first, because they should be over here, right? Low energy, mid, high energy, right? Maybe it's just for aesthetic reasons. What's the bond angle? Well, the bond angles are all 90 degrees. Octahedral, bond angles, and the next slide should have hybridization, D2sp3 hybrids. Okay. How do we know the hybridization is not sp3, right? Because if we ignore these, right, we only need 4, right? Well, the reason is experimental data tells us that it's square planar and not tetrahedral. If we only had sp3 hybridization, that molecule would have to be tetrahedral. Not only is it nonpolar, which it would be nonpolar in either case, but the other means of investigating that molecule show us that it's not tetrahedral, it's square planar. So that is justification for giving it D2sp3 hybridization rather than sp3 hybridization. All right. So that's what it looks like. All right, here's our chart. So this simplifies the whole process. I went into nauseating detail, but when you're actually using it and solving problems with it, this table will give you all the information you need. You look at the number of groups, effective pairs. I call them groups. Around the molecule, and the VSEPR tells you the geometry, the electronic geometry. And from the electronic geometry, you know that you need 2 pairs, you need 2 hybrid orbitals, SPs. 3 pairs, you need 3 hybrid orbitals, SP3. And likewise for 4, SP3, 5, DSP3, and 6, D2SP3. So you notice that if you add the superscripts for the DS's and P's, the bottom one you get 2 + 1 + 3 is 6. So that makes it a lot easier to deal with. And that gives you the electronic geometry. Then, just like before, if you want to know the molecular geometry, you just cover up the lone pairs and that gives it to you. Okay. All right. Let's do hydrogen cyanide. Trying to call me. No, thank you. He wants me to donate blood. All right, so we start, as usual, we start with our localized electron model. We've got 1 electron here, we've got 4 there, we've got 5 here. Valence electrons. So that means we have 10 electrons, carbon in the middle, nitrogen, hydrogen. All right, so we've used up 4. Now we have 6. We start from the outside and work our way in. 2, 4, 6. Okay, we've used up all of our electrons. Now we make octets. In order to make an octet around carbon without robbing nitrogen, we simply do that. Make 2 pi bonds. Okay. Now, what's the hybridization around the carbon? Well, we have two groups, which means it's linear. While we're at it, 2 effective pairs, 2 groups around the nitrogen, it's also linear, right? So that carbon has to be sp hybridized. That gives us 180 degrees, and this nitrogen is also sp hybridized. Okay. Labeling the bonds, there's 1 sigma bond on this side, there's a sigma here, there's a pi there, and there's a pi there. So this whole molecule has 2 sigma bonds and 2 pi bonds. And there's our labeling. I got carried away with animation this day. All right. So that wasn't bad enough. Let's take these examples. I'm not sure which way the animation goes. Got ammonia. We did that one already. We got carbon dioxide. We've got SO2. That'll be a new one. And ICL5. Yep, 5. And then krypton tetrafluoride. All right. So what do they want us to do with it? Bond angles and hybridization. Well, we did this one already. Right. This one is sp3 with 109.5 degrees nominal. We know it's going to be a little less. Carbon dioxide is going to be linear. So the hybridization, do they say on the central atom? Yes. So we can ignore the oxygens. On the central atom is sp hybridized because it's linear at 180 degrees. And we'll do these fresh. So sulfur is 6. Well, we've got 3 6s. That's 18 electrons. So there. That's minus 4 equals 14. 2, 4, 6, 8, 10, 12, 14. Okay. So let's write down here. Okay. We have 3 groups around the central atom, which is trigonal planar. Right? Well, we're not finished yet, actually, are we? We have to make a double bond here. Right, in order to give that an octet. Well, we still have 3 groups, which is trigonal planar, and 3 required hybrid orbitals for sulfur is 1, 2, 3. So sulfur has to be sp2 hybridized, and the angle is going to be 120 degrees. Okay. This one would be the same as the xenon tetrafluoride. It would be krypton in the middle, and it would have this. That didn't work out too well, did it? And it would have a lone pair here, and fluorine here. So this would be D2sp3 hybridized with 180 degrees, 90 degrees, 120 degrees. Okay. And this one, let's work this one out. This is 6 times 7, right? 7 valence electrons for each, since they're all halogens, is 42. So that would be iodine in the middle, and chlorine, these 5 positions, 2, 4, 6, 8, 10 minus 32 left over, 2, 4, 6, 8, 10, 12, 16, 18, 20, 22, 24, 26, 28, 30, and then a lone pair on the iodine. Let's see. Oh, why is it showed up? I think that's it. Okay. So this gives us, electronically, it gives us 6 groups, right? So this has to be D2sp3 hybridized. So where does that lone pair go? Well, it's like, it's octahedral. So it would go up here at one of the apexes. And that would give us a square pyramid as a shape. It doesn't ask us for the shape, but that's it. And if we do a square pyramid, we have the possibility of 90 degrees only. Right? Since there's one chlorine down here, but lone pair up there, so we only have 90 degrees. There's no 180. Okay. So ammonia is this one, right? SO2, sulfur dioxide, is 120 degrees, sp2. Yep. This one is, it didn't ask us for the polarity. I threw that one in for free. Oh, it says it DSP3. Oh, Oh, I'm sorry. It's my mistake. I thought it was 4. It's 2. All right, let's start over again. Just start all over again. 8 and 2 times 7 is 14. It's 22 electrons. Okay, so we have krypton, and we have fluorine, and we have fluorine here. So that's 2, 4 is 18. So 2, 4, 6, 8, 10, 12 equals 6 electrons left over. 2, 4, 6. That means around the krypton, we only have 5 groups. So that's DSP3. Hybridization. And that is a trigonal bipyramid. All right. So where do the in a trigonal bipyramid, where the lone pairs go? They go on the triangle. And we got 3 of them. And the fluorines are here and here. So that means we only have 180 degrees bond angle. Okay, that looks better. And the last one is ion pentachloride. Oh, carbon dioxide. Sorry, we did that one already. And there we go. So ion pentachloride puts the electron pair, since it's octahedral, this one goes on apex. And we only have a 90 degree at G2sp3. Okay. So this is just a rehash. Draw the Lewis structures. What's the arrangement of electron pairs in the VSEPR model? And then you specify the hybrid orbitals needed to accommodate those electrons with our chart. Now, did I put the chart in the useful information? I don't think I did. It's not that difficult, but it's not like you really need it. Got to memorize some things. Okay, what are the limitations of the localized electron model, even with hybridization introduced? Well, first of all, it incorrectly assumes that the electrons are localized on each atom, and they're only shared through overlapping orbitals. Sometimes we have to add the concept of resonance to accommodate equal Lewis structures, right? That was our first fix to the model. And then maybe it's coming up in the subsequent one. I think we encountered one Lewis structure with a free radical. We had an electron in there. It was one of the nitrogen compounds. One electron in there that had no pair, right? So we had a deficient octet. Right, that model does not adequately account for free radicals. And it actually, even though we gave you charts with bond energies, those were not actual calculated values. Those were model assumptions that this is probably where the energy is going to be. But there's really no direct calculated information for the energies of these bonds using the localized electron model. It doesn't accommodate them. And the one that I left out was the localized electron model. I need to put this one in there. Does not account for geometries that don't fit the model. And that, in order to correct that, we had to introduce hybridization. Okay, this is normally where I'd pause if we didn't have a lab today. But we can go ahead and, yeah, it's only 1:30 now. Yeah, we got time. So we're going to finish this chapter lecture today. So actually, we're done with the valence bond theory and the localized electron model and the valence shell electron pair repulsion models. And now we're gonna progress in time to a new theory that actually does allow us to calculate energies, and it accommodates a sharing of electrons in a more socialistic way. The molecules hold electrons in common, right? It's like, say, chemical communism. So this is called the molecular orbital model. Or the molecular orbital theory. And it has a model that goes with it. So the basic concept behind the molecular orbital model is that when the molecule forms, the atomic orbitals are gone. They're actually absorbed into the molecule, and the molecule forms a new set of orbitals that are common to the entire molecule. So that's fairly easy to conceptualize for small molecules, but for large molecules, it may be a little hard to wrap your mind around. We still incorporate some things that are sort of grandfathered in from Bohr's planetary orbital model. All right, so we're gonna talk about S's and P's and D's and so forth. But those are atomic orbitals. And when we create our molecular orbitals, we only use the designations for atomic orbitals in such a way that they tell us where the molecular orbitals came from. That helps us organize our chart for the molecular orbital construction. All right, so here's a side by side, the difference between the two, right? Localized electron model relies on atomic orbitals only. Molecular orbital creates new molecular orbitals. We still treat the bonding in a quantum mechanical fashion. The quantum mechanical treatment of atoms extended to molecules for the localized electron model. But for the molecular orbital, we create a whole new set of equations for the molecular orbitals. And they're applied to the entire molecule. So that may be a little, we're splitting hairs there. Until you actually get into the equations, and if we did that, you'd see they're radically different. Okay, the localized electron model assumes that the electrons are owned by the atoms that are joined in the bond, whereas the electrons in the molecular orbital model are delocalized over the entire molecule. And this idea of delocalization, I think we talked a little bit about that at the end of chapter 8. Delocalization tends to stabilize a molecule. It lowers the energy, which makes the molecule more stable, and that's desirable. So anytime you can delocalize, it's good. As far as stability goes. I mean, if you're trying to make an explosive, then maybe you don't want to do that. You just want enough delocalization to keep it from blowing up in your face. We still have 2 electrons per orbital, right? Whether it's the atomic orbitals or the molecular orbitals, we still hold to that rule. We still have quantized energy too, right? The chi-squared wave function that tells us the probability of finding an electron in a certain area of volume of space is still the term that comes out of the quantum mechanical equations, except that in the molecular orbital wave function, it has a different look to it. Let's put it that way. Okay. So always remember that when the atomic orbitals are combined to generate the molecular orbitals, the number of orbitals is conserved first, and the atomic orbitals disappear. The way we conserve those orbitals is that we create two types of orbitals. One is bonding, one is anti-bonding. And that's exactly what it means. The bonding forms the electron cloud or density between the atoms that shows that they spend most of their time between the atoms, and that secures a bond. The anti-bonding orbitals tend to form electron clouds away from that bonding volume. We'll show you some pictures in a minute. And this is based upon the concept of interference. Now, I've got some videos that are coming up, and I can get the sound coming through the speakers in the room, but there may be a glitch. When I do that, I think it stops recording, because I tried it yesterday and I had to do some fancy footwork to get pieces back together for the video. So I'm not going to try to send the sound through the speakers today. Hopefully it'll be loud enough to where you can hear it. And then of course the folks at home ought to be hearing it just fine. Okay. If the molecular orbital centers the electron probability on axis, then we still call that a sigma molecular orbital. Right? Rather, when in the localized electron model, we called it a sigma bond. But in the molecular orbital model, we call it a sigma molecular orbital. Okay. And when we draw an example on the board, then that'll put some flesh on the bones. All right, and this last statement I've already said 2 or 3 times. Can't say it enough. Atomic orbitals are consumed in the construction of the molecular orbitals.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves vibrating within the instrument, producing beautiful sounds. That's good energy.
Okay. I think of these two types of interferences, the constructive interference, like if you've got your niece sitting in a swing and you're pushing them in the swing, then if you hit it just right, they'll go higher. You hit it just right, they go even higher. And that's constructive interference. Destructive interference would be if you want to stop them, then you apply energy in the opposite direction to their motion and they slow down. I had another analogy, if I can remember what it was. But no sense wasting time. This concept of, now what we were shown there was constructive interference and destructive interference. The constructive interference would be, in our quantum mechanical equations, would lead to the bonding molecular orbitals. And the destructive interference in those equations would lead us to the anti-bonding molecular orbitals. Now, we were just watching it there in one dimension, just back and forth. This happens in 3 dimensions. So it's a bit more complicated. So when two overlapping waves encounter one another, we call they are superposed on one another. This concept of superposition. And interference happens when we consider the summation of their amplitudes. Right? So this if they are superposition gives us constructive interference, then their amplitude increases, and with destructive interference, their amplitude decreases. Now, I can imagine situations where you have 2 waves encounter each other, and they're not exactly in phase, that you would get an intermediate, either a constructive or destructive result. And we see this concept of interference used in, well, let's keep it simple, in say AM radio. So you have this carrier wave that is a certain kilohertz, which is the frequency. And then the microphone would pick up your voice, or the record player would pick up the music and send it as an electrical signal to be superposed on that carrier wave. And it would modify that wave in various ways. And then you would send it out. You broadcast it. It would be picked up on the other end. And the receiver then would apply a matching carrier wave, but with the phase would be off just far enough so that you would get interference with the carrier wave signal. And the carrier wave signal would destructively interfere in such a way that it would actually subtract out the carrier wave, and you're left with the voice or music signal that was originally added to it. That's called, well, in this simple case, it's called duplexing, right? But nowadays we do what's called multiplexing, and this happens over the internet as well. Only in that case, it's done digitally. So we won't get in too far into the weeds for that one. All right, they can form complex patterns. That's what I'm getting at. Okay, here's an example of the very simplest molecular orbital model for hydrogen. Hydrogen has a 1s orbital for each one of the atoms, right? We see the nucleus is represented by, well, actually, that's not the nucleus representation. That's the s orbital. And then when you overlap those two and create molecular orbitals for the ones on the right, then if there's destructive interference, you get the anti-bonding orbital. And the electron density profile puts the electron density out here, outside the two atoms that are bonding. If you get constructive interference in the bottom plate, part of the picture, then you get constructive interference and you get electron density between the atoms. So they work against each other, actually, in forming the bond. The anti-bonding is just that. It's against bonding. And the bonding orbital is what you want for a strong bond. So we're going to make use of that in just a few minutes. When we put these two atomic orbitals together to get the molecular orbitals, then what we find is that in terms of energy, and this is calculatable now, as opposed to the localized electron model, which cannot calculate energies, the anti-bonding orbital is at a higher energy than the atomic orbitals. And the bonding orbital is at lower energies than the atomic orbitals. That's all we're saying in this slide. So here's the way we represent it. We have our energy scale here, right? And then we have our atomic orbitals here. Yeah, let's go with hydrogen here, and then this is the molecule in the middle. So the atomic orbitals we would set up over here. This would be, yeah, okay. Two different atoms. So this would be our atomic orbital for that atom. And this would be the atomic orbital for this atom. And it would have one electron in this one and one electron in that one. Okay. When we combine them to get the bonding orbital, we would produce something up here and something down here. This would be the bonding orbital. This would be the anti-bonding orbital constructed from the atomic orbital. So now when we're at this place, those are gone and we're left with this one. Well, it turns out that this is a sigma orbital. Both of them are sigmas. Right? This one is a sigma bonding orbital from the 1s atomic orbitals. This one is a sigma anti-bonding, and we designate that with a star, also from the 1s orbitals. So notice that we started with 1, 2, and we ended up with 1, 2. So we've conserved orbitals. Now we have to conserve electrons. So we use not Hund's rule, the Aufbau principle, where the electrons go into the next available lowest energy state as we fill them up. And the lowest energy state here is that one, which can hold 2 electrons. So both of these electrons go into the bonding orbital and none go into the anti-bonding. Okay, that's good. And that helps us rationalize why dihydrogen forms, right? It forms a bonding molecular orbital for this molecule and no anti-bonding. So there's no pressure to split apart, which the anti-bonding we would rationalize that. Okay. So the molecular orbital model produces electron distributions and energies that do agree with our basic ideas of bonding. Okay. So if we were to draw this molecule, before we had any introduction to molecular orbital theory, we would say, well, we can only form one bond, right? Because we have two electrons, one electron here, one electron here. One forms a sigma, right? So we're still in agreement there with everything we knew before molecular orbitals were introduced. And the labels we try to use to designate where the molecular orbitals came from, like here, they came from the 1s's, and what they are now, which is sigma molecular orbitals. We're going to do a similar thing for pi orbitals in a few minutes. Okay, that means that the bond is on axis. And we can write out an electronic configuration for molecules now, not just atoms. Only we would use molecular orbitals for, say, if we have this one, we would write an electronic configuration of a sigma and a sigma star from the 1s and the 1s. And this one would only have 2 electrons in it. So the abbreviated form would just be that. Okay. Okay. So what if we tried fluorine, right? What would we get with fluorine? Well, that's going a little too far too fast. Right. So let's see if we can put a model together for fluorine. Well, let me see. Let me check my slides to see if I've got one coming up. Because it might look better than if I try to draw it by hand. No, I'm going to draw it by hand. Okay, so here we have our energies again. And we have our fluorine atom, and our molecule formed from those 2 atoms. We know that the electronic structure for fluorine is going to start with a 1s, right? And it's going to go to a 2s. Let's see, it's yeah, we'll put a 2s maybe right in here. And then it's going to have 3 2p's. Okay, X, Y, and Z. And on the other side, we'll have the same thing. We'll have 1s. We'll have 2s. And we'll have our X, Y, and Z for the 2p's. Okay. So these, well, let's put in our electrons too. Let's see, this is 7 each. So we have 1, 2, 3, 4, 5, 6, 7. Right? No, we need 9, excuse me. 9. There we go. It's not 7. 7 is nitrogen. There we go. So this is what we have in the atomic structure. There we go. Okay, so how do we form molecular orbitals from these? Well, we did a 1s before, so that's fairly simple. Right? Well, I need to compress it a little bit. So this is going to be a sigma from the 1s and a sigma star from the 1s. This one is going to be a sigma from the 2s and a sigma star from the 2s. And for this one, we're going to get a sigma from 2p. And up here, we get another sigma from the 2p, but it's a star. Then we get, so that's two of them. We got two more. So we have, it's two from each side. So we have four more actually. So we're going to get, here's where the pi's come in. This is going to be a pi. This is going to be a pi from the 2p. And this is going to be a pi star and a pi star from the 2p. Okay. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 molecular orbitals. All right. It's a little compressed. So to show the tie lines, these were formed from here. These were formed from here. These were formed from here and here and here and here and from there and from there and from there and from there. Okay, now we can put our electrons in. So we start, we have 2, 4, we have 18. We have 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16. So 2, 4, 6, 8. Sorry. I'm counting 2 for each one. So let's try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So if we wrote that out in longhand, then we'd have the sigma 1s, the sigma star 1s. We'd have the sigma 2s and the sigma star 2s. And then we would have the sigma from the 2p and the sigma star. Oh, excuse me. Nope. That's higher energy. That sigma star comes out here from the 2p. Then we would have the pi from the 2p and the pi star from the 2p, and then the sigma star from the 2p. There we go. That should be the correct order. No. Oh, it left out this one because there are no electrons in it. Okay. All right. So then we would say how many electrons here? 2, 4, 6, 8, 10, 12, 14, 16, 18. That's it. And then this one wouldn't be there. So this would be F2. That would be the molecular orbital structure in shorthand. Rather than drawing it out like that, this would be it. Okay. All right. Now, once we have that to go on, we can do some calculations that tell us what type of bonding can we expect. Very often, what we'll do is we'll say we're only going to build the molecular orbital model from the valence electrons. So we would just leave this one off. So if that was missing, that just means that it's assumed core molecular orbitals, and we're only using the valence molecular orbitals to tell us something about the molecule. And here's one thing that we can do with it. We can calculate the bond order. Bond order is analogous to single, double, triple. Only in our localized electron model, that's all we can have. Single, double, and triple, there's no in-betweens. But with bond order, we can get fractionals. Okay, so what we do is we take the number of bonding electrons, number bonding, minus the number of anti-bonding, and divide by 2. Okay? So if we do that for our example here, we have the number of bonding is 2, 4, 6, 10. And then the anti-bonding is 2, 4, 8. Divided by 2. So that's 2 divided by 2 is 1. So the bond order for this molecule, the difluorine, is 1, which coincides with what we know from the localized electron model as a single bond. Sometimes they agree and sometimes they don't. Okay. If we did the same thing for hydrogen, we'd come out with a bond order of 1 because it's bonding, 2 bonding electrons minus no anti-bonding divided by 2 is 1. Now, what would happen? I'm not going to redraw it up there because it's in the slide. What would happen if we made an H2 anion? We just added an electron. Where would it go? It would go in the anti-bonding orbital because that's the next highest one. And what would that do to the bond order? Now it's 2 minus 1 divided by 2 is 1/2. It would weaken the bond from a 1 to a 1/2. Oh, okay. So we got molecular orbital theory. Let's see. I wonder how long this one is. That's 13 minutes. Takes a while, but it's worth it.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have 1 electron located in the 1s subshell when in its ground state. And of course, we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when 2 atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those 2 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the 2 hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these 2 nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have 1 more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the 2 nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the 2 atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these 2 atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these 2 different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed 2 new molecular orbitals from our 2 atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, 1 from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. there's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. Now you might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching.
All right. So, what we've been looking at so far are simply diatomic molecules that are homonuclear. That is, they have the same element paired with each other, which is the simplest way to start. It's the easiest way to understand this stuff. When we get into heteronuclear molecules, then you get energy shifts that are difficult to determine. And I'm only going to introduce a couple of them just to show you how complicated it can get really quickly. There was also a concept introduced called paramagnetism. Paramagnetism is the property of a compound that when it's placed in a magnetic field, it's held there. It's attracted to the magnetic field. And oxygen will do that. I got a picture I'll show you in a second. The opposite of that is diamagnetism, in which the molecule is repelled by the magnetic field. And that's a case where all the electrons are paired. If you have at least one unpaired electron, then it will produce a magnetic field that can be attracted into the external field. And this is quantifiable. We can measure the strength of that attraction in a device that I got a picture of in a minute. And these are two examples, right? The reason we bring this concept up is because the valence bond theory and localized electron model cannot explain it, because we would expect electrons for the oxygen molecule to be all paired. And that would say that oxygen should be diamagnetic, but it's not. It's paramagnetic. And the molecular orbital theory explains that. Okay, here's a conception of a device that measures this strength of this paramagnetism. We lower the sample into an electromagnet. We know the strength of the magnetic field, and we know the pull that's exerted on it as it enters the field. We can measure that with a balance, and we can quantify whether we expect this to be due to 1, 2, 3, 4, 5 unpaired electrons. The more unpaired electrons, the stronger the pull. And here's what liquid oxygen looks like when we pour it into one of those big horseshoe magnets. Oh, Professor Dave wants to talk. Now he's going to introduce some more concepts, and we'll discuss those afterwards. I wasn't sure whether to put him first or to put them first, but he does a fairly good explanation, so I'll let him talk, and then we'll dig into this. Actually, the concept that we're going to see here is the SP mixing.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called SP mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other anti-bonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 antibonding electrons, including the sigma 1s star antibonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, there's that diagram again. And I placed this one in your review document, so you'll have it available on the exam too. But there's also another one that gives you a little bit more information. Okay, we see that the dividing line is between, say, nitrogen and oxygen. So oxygen and fluorine have no evidence of sp mixing. That places the sigma below the pi in the bonding orbitals. Where you have sp mixing, then the sigma increases in energy to the point that it's higher than the pi's. But this also shows homonuclear diatomic molecules from boron through fluorine, and gives their electronic structure, the molecular orbital structure, and whether or not they're paramagnetic or diamagnetic, and that should be easy to determine from looking for unpaired electrons. Like diboron is paramagnetic because you see the 2 unpaired electrons there. And bond orders calculated, bond energies are given, and bond lengths are given also. I couldn't get that out of, I just left it in there. Okay. Some authors call this sigma pi mixing because SP implies atomic orbitals, whereas sigma pi implies molecular orbitals. So it's proper to say sigma pi mixing, but SP mixing is kind of stuck. Okay, so here's an example of a heteronuclear diatomic molecule of 1 carbon and 1 oxygen. That's carbon monoxide. And notice that the carbon atomic energies start higher than the oxygen energies, and that makes sense because the oxygen has a higher nuclear charge. Right? Oxygen has 8 protons, carbon only has 6. So we should see the beginning position as oxygen's lower than carbon. And then when we put that molecule together, it's difficult to tell whether you should expect SP mixing or not, because carbon's on one side of that dividing line, oxygen's on the other side. So you're going to have to be told at this stage. I mean, we can't figure it out because we don't have the background to do it. But what we see here is that, let's see, we don't have mixing because the sigma is below the pi bonding orbitals, right? There's no mixing here. So we're assuming that probably because the oxygen has such a high nuclear charge that the mixing doesn't occur. So the order is the same, and then we just fill the orbitals up as we would expect. But what we also see is, and we've discussed this before in terms of electronegativities, we should expect that bond to be slightly polar because carbon is to the left of oxygen. Oxygen is more electronegative, so the electron should spend a little more time close to the oxygen, right? And if you look at the molecular orbital diagram, you see that the electrons reside, for the most part, in lower energies than the carbon. That lower energy clue should tell you that they're probably going to spend more time to the oxygen because it contributed the low energy side, and they're going to be on that side. So this is a polar bond, probably. Let's see. HF is even more pronounced. So if we see the HF molecular orbital diagram, we see that the hydrogen 1s is way, way up there, and the 2p that is combined with the 1s to give you the molecular orbital sigma and sigma star, you'll see that the electrons are residing much closer to the fluorine side in energy. So that is also a clue that this is probably a very polar bond. Let's see. And if we do the calculation, we find that the bond order is 1, which is what we should expect. And this is an artist's idea of, how are the electrons distributed? Oh, that brings up another point. When we were considering the valence bond theory with the localized electron model, and if the electrons are considered a property of each of the atoms, then the tendency there is to consider electrons in not so much the wave nature, but the particle nature. Because if they're orbiting the sun rather than orbiting Betelgeuse, then we would expect them to be particles. But when we get into the molecular orbital situation, the electrons are delocalized over the entire molecule, and it's more difficult to assign particulate nature to an electron in the molecular orbital model than it is in the localized electron model. Just one of the fringe benefits, I think. Okay, let's see. I think I duplicated that slide, didn't I? Well, maybe not. Just emphasizing the polarity of the bond between hydrogen and fluorine. This delocalizing also is a stabilizing factor. So for those molecules that we've required resonance in the past, now we don't have to use that, because with the electrons delocalized over the entire molecule, then the model doesn't even lend itself to the necessity of resonance. We don't have to resonate between different structures. We have one structure that's described by the molecular orbital model. Okay, so sometimes it's convenient to, I guess the word would be hybridize the localized electron model and the molecular orbital model. If we go to something like benzene, where we have, if we approach it from the localized electron model idea, then we have to have doubles and single bonds, right? But benzene, we know, has equal bond lengths throughout that ring, right? So we know that it's not double single, right? Double would be shorter and single would be longer. And that would be unstable too. So we know all the bond lengths and bond energies are the same between each of the carbons in that ring. And the necessity for resonance here is negated if we induce some delocalization, right? So we can hybridize in this way, and then when we delocalize with the sp2 would leave one unused p orbital. If instead of saying p orbital overlaps between two molecules, we just delocalize all that p orbital nature to the ring, the whole ring, then we can put those 6 electrons that would normally go into 3 double bonds and put it in that ring structure, that delocalized ring structure, and that would stabilize the molecule. And in fact, benzene is a very stable molecule. And this is what it would look like. This, in fact, is an example of a conjugated system. When you have, well, actually, this model is aromatic. Aromatic is a type of ring structure that adds stability to molecules. And we're not going to go into a lot of detail there until you take organic chemistry. But for long molecules that have alternating single and double bonds, like that, you get this delocalization over that entire structure. And that's called conjugation. Conjugated bonds are much more stable, and we can quantify their nature by measuring their light absorbance profile. And we find that the more of these that are in a molecule, the lower the energy that is absorbed. So that means that they're more stable. It doesn't take as much energy to be absorbed to resonate with this system. So you see molecules like well, let's see, vitamin A, right? Vitamin A for vision, right? Has a conjugated system, and it absorbs in it actually absorbs, but emits in the orange. We see the orange, but it absorbs in lower wavelengths, longer wavelengths. Crustaceans that turn red, like crawfish, lobsters, crabs, they have a much longer conjugated system. And that gives them a lower emission spectrum that gives you the red rather than the orange. So this is all due to delocalizing electron density. If you can do that, you stabilize the molecule, and it can be used in other, right? We had the nitrate molecule that we drew under the localized electron model. The nitrate molecule, we had to resonate it with 3 different structures. That's because the model doesn't allow for partial bonds, but molecular orbital does. Right. I think I showed you this sort of a halfway bond model. But when we use the molecular orbital system and we hybridize, we delocalize electrons throughout that pi system, then we get a stabilized molecule. The nitrate is a very stable molecule. The nitrate ion is very stable. This is NO3 minus. Now, the last slide is just to illustrate that there is physical evidence. There's measurable evidence for this molecular orbital theory. We can determine the relative energies of electrons in individual atoms and molecules. And what we do is we take the molecule and we fire high energy photons at the sample. And the energies are absorbed by the electrons in the system, the whole molecular system, and then re-emitted at different wavelengths with given energies. So if we fire a certain energy photon in and it emits light of a certain wavelength, we can calculate that energy, which I think we've done in this class. But then we measure the kinetic energy that's left over. And that kinetic energy tells us the stabilization factor, I should call it, for the system. And then when we plot that out in that graph on the right, we find that these measured amounts of energy coincide with the calculated values for the molecular orbitals. So that's just confirmation that the theory is valid, at least as far as we can tell. And that's what we do with theories. We collect physical evidence and we see if it matches with the theory. And if it matches with the theory, then we think, okay, we're on the right track. And when it doesn't match, we say, why not? And if we have to, we'll tweak the theory. If it's so bad that we can't tweak the theory anymore, then we get another theory. Okay, I think that's the last slide. Yep.